Okay, good morning, everyone. I want to welcome you to another theory of statistics class. Of course, I'm actually going to say this, it's getting complicated, okay? And I will actually advise you pay more attention in case you do not understand, make sure you ask me a question. Today we're going to be going into what I call movement and movement generating functions. Before now, okay, I walk you through some selected discrete probability distributions. And let me tell you this, what we've been doing, we don't just do what we do. There's a reason why we do what we do. If we want to understand the movement of random variables in a probabilistic space, of course, we need probability distributions. I'm going to say that again. If we want to understand, okay, the behavior of random variables, the movement of random variables, when I talk about random variable, I could talk about income, I could talk about age, I could talk about anything that varies, okay? Now, the random variable, if I really want to understand the behavior, I need a probability distribution. I remember I walk you through the discrete type probability distribution, like the binomial, geometric, negative binomial, and so on, like that. But let me tell you this. Today, we want to go through some kind of formulas that will enable us to describe our, to understand our probability distribution the more. Okay, so in a probability distribution, we actually look out into so many statistical interests. In a probability distribution, I want to understand the average. I want to understand the variance. I want to understand the skewness. I want to see if there's a departure of the distribution of my data from normality, which is called skewness. I also want to understand the tail behavior of my distribution that we call kurtosis. So I'm going to walk you through some kind of measures. Now, let me tell you this. The first raw moment, okay, is the average, is the mean, okay, that we call location, okay. So the first raw moment, okay, is actually that. The second central moment, like here, if I'm talking about the first, I'm talking about this guy, expected value of S is the first raw moment, okay? The second central moment, okay, the second central moment is actually this guy. The second central moment is, will give us the variance. The second central moment is the variance. So I may be interested in figuring out how data spread, okay, from the mean. So if I want to measure variability, I'm going to use the second central moment. Now, the third central moment, okay, the third central moment, which is this guy, okay, we actually point to the direction of the skewness. Like, this is going to be the numerator for skewness formula, okay? That will serve as numerator for skewness. this is not skewness, but a numerator for skewness. Now, the fourth central moment, okay, which is expectation of x minus mu raised to power 4, okay, that will serve as numerator for kurtosis. Now, let me tell you this. There are 4 important things that we want to know about as far as distribution is concerned. Okay, I care about the mean, I care about the average, I care about the variance, I care about the skewness, I care about the kurtosis. Okay, now understanding movement, of course, we'll be able to understand that. Now, I want to start, from the family, okay? I want to start from the family, and I actually need you to pay attention, okay? I need you to pay attention on how this is actually going to be done. Now, I want to first start from the family. I want to start from raw movements. Okay? Now, you know the significance of movement. Without movement, we may not be able to find the mean, we may not be able to find the variance, we may not be able to find the skewness, we may not be able to find the kurtosis from our distribution. But you know what? I actually want to start from the family. Okay? There's something I call raw movement. Okay? The raw movement, okay, we also call that movement about zero. Okay? It's also called movement about. We call it movement about zero, or you call it movement about origin. Okay, we call it movement about zero, we call it movement about origin. Take a look at this. The formula is going to be this, which is going to be this. Now, why do we call this? If you take a look at this and this, it's like mu equal to 0. I'm plugging in mu to be 0 here. So this is movement about 0, or movement about the origin. Now, what is of statistical interest, we want to consider R1, 2, 3, and 4. Now, when R equal to 1, okay, I have the mean. This is the mean. Okay, the first raw movement is the mean. Now, when R equal to 2, I have the second, okay, I got the second one, okay. When you take a look at it, the second one, expected value of S squared is called, that is the second raw movement, okay. If I want to find the variance, you remember the other time here, if I want to find the variance, when we're deriving the distribution, we make use of the second raw movement minus the square of the first raw movement. If I want to get the variance using the raw movement, I have to use the second raw movement minus the square of the first raw movement. Okay, so now expected value of S squared. Okay, so what I actually mean here is, putting square on that. And of course, we also have third moment. So this is second raw moment. Okay, so this guy is first raw moment. Okay, then expected value of x cubed, the third. Okay, the third raw moment, and the expected value of x4, fourth raw moment. So what is of statistical interest? We actually want to know what is the expected value of s, what is the expected value of s squared, what is the expected value of s cubed, what is the expected value of x4. Now, let me tell you this. If x that we're talking about is a random variable, if it's a discrete random variable, if x that we're talking about is a discrete random variable, okay, if s is discrete, okay, the first one is going to be summation x multiplied by the probability. Okay, the second is going to be summation s squared multiplied by that. The third raw moment is going to be summation, this, multiplied by that. The fourth, okay, is going to be summation, x4 multiplied by that. Okay, if I now want to generalize, generalizing, okay, okay, I'm actually going to say expected value of this raised to power that is going to be this. Take a look at that. That's a generalization. So here, if S is discrete, okay, now if S is discrete, okay, so that's exactly what is seen here. Take a look at that. Expected value of S is this guy. When S is discrete, I'm actually using that, okay? And if I want to get a variance, I'm actually going to make use of this. You can see in the last class, we were using this to get a variance, which is going to be the difference between the second raw moment minus the square of the first raw moment. Now, I quickly want to walk you through an example now. Please pay attention. I want to walk you through an example now. Okay, now you are given this table. You have the random variable S and the corresponding probability. Okay, and they want you to figure out the average. Of course, the mean, you're going to, and S is discrete in this case because 2, 3, 4 up to 12, that's a discrete number. Of course, I'm actually going to use this guy. And what I'm going to do is to multiply. So what I'm going to do is just multiplying this by that by that, all the way. Then I'm going to add them up. Then you're going to end up in getting 7. Okay? You're going to end up in getting that. So what we've done, we've used this formula here. Okay? Now, if I now want to find the variance, of course, I walk you through how to find the variance the other time. Okay? Expected value of S squared, it means I'm going to use this guy, minus the square of the mean, okay? And when you do that, you're actually going to get 35/6 for that table. I think I walked you through stuff like that before. Now, the next thing I want to talk about, I just talked about the raw movement. I also want to talk about the central movement. These are raw movement. The raw movement, they also call movement about the zero or about origin. Okay, I want to go into another one now. Okay, I want to go into the the central movement. Okay, and I need you to pay attention. Okay, I want to talk about central movement. Okay, when I want to talk about central movement, okay, the general formula is going to be this guy. That's the general formula for central movement. Okay, when I plug in mu to be 0, that will take me back to the raw movement that I just talked about. Now, we are also interested in when R equal to 1, 2, 3, or 4. That's what we're interested in. Now let's take a look at that. What is this? When I plug in 1, what does that become? This is first central movement. First central movement is 0. It's always 0. This guy is going to be 0. This is expectation of a deviation. That's going to be 0. Okay. Now the second central movement. Okay. The second central movement. Okay, is the variance. If I want to get variance directly, I'm actually going to use this guy. The second central movement is the variance. Okay, the third is going to serve as what is going to be the numerator for the skewness. Okay, third central movement. Okay, that will serve as a numerator for skewness. The fourth. Okay, fourth central movement, That will serve as a numerator for kurtosis. Numerator for kurtosis. Now, this is the first four central movement. The first central movement is 0, always 0 for any distribution. The second central movement is the variance. The third central movement is the numerator for skewness. The fourth central movement is actually going to be the numerator for kurtosis. Okay, and you know what? If S is also discrete, okay, please pay attention. If S is discrete, okay, and I want to find the second central movement, I want to find this guy. It's going to be summation, this guy squared the probability. For instance, if S is discrete and I want to find the second movement, okay, do you know that when you simplify this guy is going to give you this guy. It's going to give you that. When I simplify that, I'm going to arrive at that. Okay? I'm actually going to arrive at that. Okay, now, in general, expected value of x minus mu raised to power r, if S is discrete, I'm actually going to have this guy. That would be the general formula for situation where S is discrete. Now, I've talked about raw movement. I've talked about central movement. Now, and I want to talk about standardized movement. Standardized movement. Okay? I want to go into standardized movement right now. I want to go into standardized movement. Okay? Standardized movement. Now, I need you to pay attention. We've been talking about different kind of movement. Okay, I want to talk about standardized movement. Okay, the general formula is, when I say standardized, Z score is x minus mu over standard deviation. We normally make use of Z score in a situation where I actually want to scale my data set. I want the data to have the mean of 0 and the variance of 1. Okay, now if Z equal to that, then expected value of Z raised to power r. Expected value of Z raised to power r is a standardized R moment. Now, I'm also interested in getting the value of the standardized moment when R equal to 1, 2, 3, and 4. When R equal to 1, let's take a look at that. When R equal to 1, I'm actually going to have this, which is the same thing as this. And you know what? Can somebody tell me? What would this guy give? 0. You said that. You said 0? Send me a message. Because the numerator is 0. The first standardized moment is 0. And this is how we know that the mean of a standardized random variable is actually going to be 0. Okay? Now, if I go to the second standardized now, the second standardized is actually going to be this guy, R squared. Can somebody tell me? What is it going to be? This one? What is it going to be? 1. How? I'm going to show you. Expectation of x minus mu squared divided by sigma squared. This guy here is also variance. You remember this guy? This is a second, second central moment. So this is also sigma squared. So sigma squared divided by sigma squared, that's going to be 1. You see that? So the second standardized moment is actually 1. The first standardized moment is 0. The second standardized moment is actually 1. Now, let's take a look at the third one. The third standardized moment, okay, the third standardized moment, okay, which is if you have this guy. Oh, my God. If you take a look at this, okay, the numerator here, is the third central moment. So everything here, this is called skewness. Everything here is skewness. If I want to know the degree of departure of my distribution, the distribution of my data from normality, I'm actually going to use the third standardized moment. This third standardized moment is the skewness. If I want to find skewness from a distribution, I'm actually going to use that. What is the fourth one? Let's see the fourth one now. Okay, we're going to see the fourth one now. Okay, the expectation of z raised to the power 4, which is the x minus mu, this raised to the power 4, which is expectation, x minus mu raised to the power 4 by sigma 4. Okay, this is kurtosis. If I want to understand the tail behavior, okay, the tail behavior of my distribution, I'm actually going to use kurtosis. Skewness and kurtosis become very essential in finance because the behavior of financial data is leptokurtic. It's not normally distributed.